ಒಂದು ನಿಮಿಷ ಅಂತ
ಒಂಜಿ ಮಾತ್ರ Good afternoon, students. Today we are going to discuss about the S-block elements. In the S-block elements, I left one topic, that is salts of oxo acids. Salts of oxo acids. Salts of oxo acids. So before studying about the salts of oxo acids, oxo acids are nothing but protonated hydroxyl group and the oxo group. Protonated hydroxyl group and the oxygen group is directly attached to one element. So the total molecule is nothing but an oxo acid. For example, H2CO3. H2CO3, I can write it as CO and OH twice. COOH twice. Where hydroxyl group, protonated hydroxyl group is directly attached to the carbon atom and oxygen group is attached. So this is nothing but an oxo acid. Another example, sulfuric acid, H2SO4, sulfuric acid. In the sulfuric acid, sulfur is an element, oxygen O3H2. Protonated hydroxyl group is attached to the sulfur. That sulfur is attached to the oxygen atom. So that is an oxo acid. And let me give one more example, HCl, hydrochloric acid. Hydrochloric acid is not an oxo acid because OH group and oxygen is not present in the hydrochloric acid. That's why HCl is not an oxo acid. Now let us discuss about the salts of oxo acid. Salts of oxo acid is nothing but group 1 element. Group 1 elements are lithium, sodium, potassium, rubidium and the cesium. These elements, these metals, when combining with the oxo acids like carbonic acid, let me write a reaction with the lithium reacting with H2CO3, reacting with the carbonic acid. It gives the lithium carbonate, that is Li2CO3. Lithium carbonate plus hydrogen gas get liberated. And in your syllabus, only the carbonate salts of oxo acids is mentioned. That's why I am explaining only the metals, group 1 metals reacting with the carbonic acid. Lithium reacting with the carbonic acid, it forms a lithium carbonate. Sodium carbonate, rubidium carbonate, cesium carbonate is formed. Now, within these carbonates, down the group, stability increases. Down the group, stability increases. And why this stability is increases? Due to mainly the size factor. We know that down the group, atomic size is increases from the lithium to the cesium. Atomic size is increases. Carbonate ion size is bigger one. Size of the lithium ion, Li plus ion, is a smaller one. So the force of attraction, I mean the bond formation between the smaller ion with the bigger ion, that bond is the weaker bond. As we move down the group from the lithium to the cesium, atomic size increases, so the bond formation between the cesium and with the carbonate, that is a stronger bond. So down the group stability increases. That's why lithium carbonate Li2CO3 is less stable to heat. It is less stable to heat. When it is heated, I mean lithium carbonate, when it is heated, it gets decomposed. It forms lithium oxide plus carbon dioxide gas is liberated. Lithium oxide and carbon dioxide. Down the group, this carbonate stability will be increases, and almost all these carbonates they are soluble with the water. They are soluble with the water. They are soluble with the water. And it may form, that is, all these metals reacting with the carbonic acid, it forms lithium hydrogen carbonate, sodium hydrogen carbonate. I mean metal hydrogen carbonate is also forming MHCO3. Between this metal hydrogen carbonate and with the lithium, metal carbonate, between the metal carbonate and with the metal hydrogen carbonate, between these two, metal carbonate is the most stable one than this one. Metal hydrogen carbonate is most stable than the carbonate salt. So these are about the salts of oxo acids of group 1 metals. Next, let us study about the group 2 elements salts of oxo acids. Group 2 elements salts of oxo acids. The first one reacting with all the metals, reacting with the carbonic acid, all the metals reacting with the carbonic acid, metal plus carbonic acid, it gives rise to metal carbonate. Metal carbonate is nothing but MCO3. And down the group, again the same property, down the group stability of these carbonates, stability of the carbonates increases. It is increases. Down the group, stability of these carbonates get increases. And all these carbonates are insoluble in water. All these carbonates are insoluble in water. Second one, all these metals reacting with the sulfuric acid, all these metals reacting with the sulfuric acid, it forms metal sulfate. Metal sulfate is nothing but MSO4. Metal sulfate plus hydrogen gas get liberated. All the metals reacting with the sulfuric acid, it forms metal sulfate plus hydrogen gas get liberated. And down the group, and all these metal salts are stable one. Down the group stability will be increases. The last two metal sulfates, like the metal sulfates, metals are beryllium, magnesium, calcium, strontium and barium. Strontium sulfate and the barium sulfate, they are insoluble in water. They are insoluble in water, and these sulfates, I mean the beryllium sulfate, magnesium sulfate and the calcium sulfate, they are soluble with the water. They are soluble with the water. That is about the sulfates. Third one is nitrate salts. Nitrate salts. Nitrate salts. All these metals reacting with the nitric acid, all these metals reacting with the nitric acid, which one is it? All these metals reacting with the nitric acid, it forms metal nitrate MnO3 twice plus hydrogen gas get liberated. All the metals reacting with the nitric acid, it forms metal nitrate, and these metal nitrates are stable one. I mean down the group again the stability will be increases, as well as these nitrates are present as a hydrated form. They are present with the 6 moles of water. MnO3 twice dot 6H2O will be present. So these are about the carbonates of salt, sulfates of oxo acids and nitrates of oxo acids of group 2 elements. So this is about the sorts of oxo acids of group 2 elements. Next, in the last online class, while writing the reaction with the calcium oxide reacting with the D2O, I said that CaOD twice plus D2 gas get liberated. Make the correction of that one. That is calcium oxide reacting with the D2O, whatever it may be the metal oxide reacting with the heavy water, it forms respective deuterated oxides, that is calcium oxide reacting with the D2O, it forms CaOD twice. Make the correction of that. D2 gas will not be get generated. That is heavy water chemical properties. Next, the new topic. Next is the new topic, that is redox reaction. Redox reactions. Redox reactions. See, almost all the reactions which are occur in the nature, all the reactions are considered as a redox reaction. Almost all the reactions which are occur in the nature are considered as a redox reaction. Best example is a process or the burning of the fuel. Mainly during the burning of the fuel, hydrocarbons combining with the oxygen, it liberates the energy. See, during the formation of the products as well as the byproducts, oxidation reaction and the redox reaction taking place. So almost all the reactions occur in the nature considered as an redox reactions. And now I am going to explain the definitions for oxidation reaction and the redox reaction. Oxidation reaction and the redox reaction. Oxidation reaction. So there are 3-4 definitions are there to explain the oxidation reaction. Explanation of the oxidation reaction. First one is any element combining with the oxygen. Any element combining with the oxygen, it forms the product. See, the reaction which involves the addition of the oxygen is nothing but oxidation reaction. Any reaction which involves the addition of the oxygen is nothing but an oxidation reaction. For example, carbon reacting with the oxygen give rise to carbon dioxide. Carbon reacting with the oxygen give rise to carbon dioxide. Addition of the oxygen taking place. That's why this reaction is called as an oxidation reaction. Let me give one more example. Magnesium reacting with the oxygen give rise to magnesium oxide. Magnesium reacting with the oxygen give rise to magnesium oxide. This is also an oxidation reaction because the addition of the oxygen taking place. That's why it is an oxidation reaction. One more example. CH4 plus O2 give rise to CO2 plus H2. If you balance the chemical equation, 2O2, 2H2, methane when it is subjected to the combustion process, that is addition of the oxygen, give rise to CO2 plus 2H2. This reaction is also an oxidation reaction. Now the question is, see, whatever the examples I have given, these reactions involve in the addition of the oxygen. But some other reactions, in some of the reactions, oxygen gas is not involved in the chemical reaction. If the oxygen is not involved in the oxidation reaction, is it not the oxidation reaction? That is the question. If the oxygen is not involved in the reaction, is it not that is the oxidation reaction? Yes, that is the oxidation reaction. So, one more definition for the oxidation reaction is if any electronegative element is added to the reaction, addition of the electronegative element. We know that group 17 elements are considered as an electronegative element. So, sodium reacting with the chlorine give rise to sodium chloride. Sodium reacting with the chlorine give rise to sodium chloride. Addition of the chlorine taking place, we know that chlorine is an electronegative element. That's why this reaction is also an oxidation reaction. One more example, magnesium reacting with the fluorine give rise to magnesium fluoride, MgF2. Magnesium fluoride is formed. 2Mg MgF2. Magnesium plus fluorine give rise to magnesium fluoride. Addition of the electronegative element taking place. Addition of the electronegative element. That's why this is also an oxidation reaction. That is the second definition. Oxidation reaction is nothing but addition of the most electronegative element. Is nothing but an oxidation reaction. Or one more definition, removal of the hydrogen. Removal of the hydrogen is also an oxidation reaction. Let me take the same example, that is CH4 plus 2O2 give rise to CO2 plus H2O. From the methane molecule, hydrogen atoms, hydrogen molecules are removed. That's why this is an example for, or this is an oxidation reaction. Oxidation reaction is nothing but removal of the hydrogen molecule is also an oxidation reaction. So that are the three definitions. One is addition of the oxygen, removal of the hydrogen. See, in this example, CH4 plus 2O2 give rise to CO2 plus H2O. Hydrogen is removed from the methane molecule. That's why it is an example for the oxidation reaction also. ಎರಡು ಡೆಫಿನೇಷನ್ ಅಲ್ಲಿ ಹೇಳಿದ್ರೆ, because one is addition of the oxygen, another one is a removal of the hydrogen molecule from the reaction. Here the removal of the hydrogen taking place, that's why it is also an oxidation reaction. Otherwise, using these two definitions also I can say that is addition of the most electronegative elements. Addition of the most electronegative elements are nothing but the oxidation reaction. Now, the opposite reaction, that is reduction reaction. Reduction reaction. Reduction reaction is nothing but the addition of hydrogen to an reaction. To the reaction, addition of the hydrogen taking place. For example, CH2 double bond CH2 ethane, when hydrogen is added, it gives rise to CH3 single bond CH3. Ethane molecule is formed. This is nothing but an reduction reaction. Ethane plus hydrogen give rise to ethane, addition of the hydrogen. Addition of the oxygen is nothing but reduction, oxidation reaction. Addition of the hydrogen is nothing but a reduction reaction. Or removal of the oxygen, that is from the magnesium oxide, when it is heated, it gets decomposed to form magnesium oxide. It gets decomposed to form magnesium plus oxygen. When magnesium oxide undergo decomposition, during the heating, it forms magnesium plus oxygen. Here, oxygen molecule get liberated, or the oxygen molecule is removed. Therefore, this reaction is nothing but an reduction reaction. Removal of the oxygen molecule is a reduction reaction. Or using this definition, addition of the electronegative element is nothing but an oxidation reaction. Addition of the electropositive element is nothing but an reduction reaction. I can take the same example, that is sodium reacting with the chlorine give rise to sodium chloride, NaCl. Sodium reacting with the chlorine give rise to sodium chloride. That is Sodium is the electropositive element. Addition of the electropositive element to the reaction is nothing but the oxidation reaction. If you look at this reaction, I said this one is nothing but the oxidation reaction, this one is nothing but the reduction reaction. Addition of the electropositive element is nothing but the reduction reaction. Addition of the electronegative element is nothing but the oxidation reaction. So, one undergo oxidation reaction, another one undergo reduction reaction. So, both the reactions, oxidation reaction and the reduction reaction taking place simultaneously. That's why this reaction is nothing but an redox reaction. Another example, magnesium reacting with the chlorine give rise to magnesium chloride, MgCl, magnesium chloride. Magnesium reacting with the chlorine give rise to magnesium chloride. It is also nothing but an redox reaction where the addition of the electropositive element taking place. Electropositive element is nothing but the magnesium. Electronegative one is nothing but the chlorine. So one is oxidation, another one is the reduction. Both the reactions taking place simultaneously for the formation of the magnesium chloride. So that is an redox reaction. So the three definitions for the reduction. Next, redox reaction using the electron transfer reaction. Using the electron transfer reactions. Electron transfer reactions also we can define the oxidation reaction and the redox reaction. Let me take a very simple example. Already I have studied that reaction in the Born-Haber cycle. Formation of sodium chloride. When sodium metal reacting with the chlorine gas give rise to sodium chloride, NaCl. So this is an example for the formation of the sodium chloride. See, this reaction I said I have taken the same example, one for the oxidation reaction, another one is for the redox reaction. Both the reactions are taking place simultaneously. Even using the electron transfer reaction also, I can explain the oxidation reaction and the redox reaction. When sodium atom loses the electron, it gives rise to Na plus ion plus 1 electron. Sodium loses its electron, it forms Na plus ion plus 1 electron. Chlorine atom which gains the electron lost by the sodium atom is given, that forms Cl minus ion. Now Na plus ion plus Cl minus ion combined to form NaCl. NaCl. So one is oxidation reaction, losing of the electron. Losing of the electron is nothing but oxidation reaction. Gaining of the electron is nothing but a reduction reaction. Losing of the electron is nothing but oxidation reaction. Gaining of the electron is nothing but a reduction reaction. So both oxidation reaction and the reduction reaction taking place simultaneously, it forms a redox reaction. And using the oxidation reaction and the redox reaction, we can identify the oxidizing agent and the reducing agent. Sodium undergo oxidation reaction, that is for the chlorine atom. That is for the chlorine atom. That's why sodium atom acting as an sodium loses its electron, it forms Na plus 1 electron. So that reaction is nothing but the oxidation reaction. This oxidation reaction is taking place due to the chlorine atom. That's why sodium atom is acting as a reducing agent. Chlorine atom gains the electron, that is due to the sodium atom. That's why chlorine atom is acting as an oxidizing agent. So the atom which undergoes the oxidation reaction, that is nothing but the reducing agent. That atom or that molecule is acting as a reducing agent. Any atom which gains the electron during the reaction, that reaction is nothing but the reduction reaction. That atom or that molecule is acting as an oxidizing agent. So oxidation reaction, reduction reaction. Opposite, I mean the atom which undergoes the oxidation reaction, it is acting as a reducing agent. The atom which undergoes reduction reaction is nothing but it is acting as an oxidizing agent. And one more definition for the oxidation reaction and the reduction reaction is increasing in the oxidation state. Increasing in the oxidation state is nothing but oxidation reaction. Increasing in the oxidation state is nothing but, see the sodium, it has got the oxidation state of 0, it shows the oxidation state of +1. 0 to +1 is nothing but the increasing in the oxidation number. So Na 0 to +1, that is the oxidation reaction. Increasing in the oxidation number is nothing but oxidation reaction. Decreasing in the oxidation number, that is chlorine atom, 0 oxidation state, give rise to Cl minus. Decreasing in the oxidation state, -1. 0 to -1 oxidation state is nothing but a decreasing in the oxidation state, that is a reduction reaction. So increasing in the oxidation state is nothing but oxidation, decreasing in the oxidation state is nothing but the reduction reaction. So oxidation reaction and the reduction reaction taking place simultaneously. That's why this reaction is considered as a redox reaction. Next, next is competitive electron transfer reactions. competitive electron transfer reactions. Competitive electron transfer reactions. Competitive electron transfer reaction is nothing but between the two metals, which metal is more reactive, which metal is less reactive, you need to study. Let me take an example of copper sulfate solution. Copper sulfate solution. This one is a copper sulfate solution. What is the color of the copper sulfate? That is a blue color. And inside the copper sulfate solution, you need to dip the zinc rod. Copper sulfate solution is taken inside the beaker, and in which the inside that zinc rod is dipped. Copper sulfate solution is nothing but Cu2 plus ion. I mean copper sulfate salt is dissolved in water. It forms Cu2 plus ion plus SO4 2 minus ion. Cu2 plus SO4 2 minus ion is formed in the solution. That's why it gives the color of the solution. When zinc rod is dipped into the solution, zinc metal which is present in the zinc rod undergo ionization. I mean it is ready to give the electron. It gives rise to Zn2 plus 2 electron. This reaction is nothing but the oxidation reaction. Oxidation reaction. Cu2 plus ion present in the solution. Cu2 plus ion present in the solution. It gains the 2 electron. It gives rise to copper. I mean copper metal will be formed. So between the zinc rod and with the solution, reaction will be taking place. So on the surface of the zinc rod, deposition of copper metal taking place. So the color of the copper sulfate solution little bit faded. It gets faded. That is due to the Cu2 plus ion which is present in the solution, which gets deposited on the surface of the zinc rod. That is due to zinc undergo ionization, give rise to Zn2 plus 2 electron. Whatever the 2 electron which is formed into the solution, it was gained by the Cu2 plus ion plus 2 electron give rise to copper. See, this reaction is nothing but the reduction reaction. So, oxidation reaction and the reduction reaction taking place within the solution. At the end, all the blue color solution, it forms a colorless solution now, and on the surface of the zinc rod, completely copper get deposited. See, this one is a copper deposition. Taking place. And this one is nothing but, the solution is a zinc sulfate solution. ZnSO4 solution is formed. Now we need to confirm that all the copper which is present in the solution was deposited on the surface of the electrode. That is by treating with the hydrogen sulfide solution or the hydrogen sulfide gas. When hydrogen sulfide gas or the solution which is reacting with the Zn2 plus ion which is present in the solution give rise to zinc sulfide, ZnS is formed. It is nothing but white precipitate. White PPT will be forming. Here white precipitate will be forming. It won't form the black color precipitate. Black color precipitate is due to the copper sulfide formation, Cu2S. Here Cu2S formation agudilla. Here it is forming the ZnS. So it shows that all the copper which is present in the solution was deposited on the surface of the electrode. Not the electrode, on the surface of the zinc rod. Now, between the zinc and the copper reaction was happened. Sulfate ion which is present in the solution, it is present as it is only between the zinc and the copper. Between the zinc and the copper, if you compare the reaction, zinc is more reactive than the copper. That's why zinc is ready to give the electron. After that, copper gains the electron. electrons. So in between both are metals only, zinc as well as a copper, both are metals only. In between these two, zinc is more reactive than the copper atom. That is a competitive electron transfer, competition between the zinc and the copper. Next, let me continue with the same example, that is in between the zinc and the copper, now I am taking the second example, that silver nitrate solution, AgNO3 solution. Silver nitrate solution is taken inside the beaker, and the silver nitrate solution, it is a colorless liquid. It's like a water, it will be present. And inside the silver nitrate solution, copper rod is dipped. This one is a copper rod. Copper rod is dipped inside the silver nitrate solution. See, the silver nitrate solution is nothing but silver nitrate crystals are dissolved in the water. It forms silver Ag plus ion plus NO3 minus ion. Ag plus NO3 minus ion will be formed. Within the copper rod, it undergo ionization. It get ionized. It forms Cu2 plus 2 electrons get liberated. The liberated electron, that is Ag plus 1, it gains the electron. It forms silver. So now the second diagram is little bit color is formed. That is due to the copper which is present in the copper rod goes to the solution now. Cu2 plus getting Cu2 plus. And the electron liberated was gained by the silver ion. So the silver metal is formed, which will be deposited on the surface of the copper rod. At the end, completely it returns to the blue color solution. It is a blue color solution. On the surface of the copper rod, complete deposition of the silver taking place. If you add H2S solution into the Cu2 plus ion, into the solution which containing the Cu2 plus ion, it forms a Cu2S, copper sulfate is formed, which is a white color precipitate. White color, that is white. It forms the black color PPT, black color precipitate will be forming. So hydrogen sulfate reacting with the copper, it gives rise to copper sulfate, which is a black precipitate. So while adding the H2S solution into this one, it forms a black color precipitate. Black PPT will be forming. This one is a blue color solution. To the blue color solution, while adding the hydrogen sulfide solution, it forms a black color precipitate, that is due to the copper sulfide formation. Now we can conclude one reaction. Before concluding, I want to say which one is oxidation reaction, which one is a reduction reaction. Copper undergo oxidation give rise to Cu2 plus 2 electrons. So this is an oxidation reaction. Ag plus it gains the electron, it gives rise to reduction reaction. So oxidation reaction and the reduction reaction taking place simultaneously. That's why this reaction is nothing but an redox reaction. Now I am going to conclude the reaction. See, in between the zinc and copper, I said zinc is more reactive than the copper. Now between the copper and the silver, copper is more reactive than the silver. Now zinc is more reactive than the copper than the silver. That's why zinc is ready to give the electron to the copper. Copper is ready to give the electron to the silver. Ulta reaction will not be taking place. Ulta reaction in the sense silver giving the electrons to the copper. No. Only zinc can give the electron to the copper. Copper will not give to the zinc. Zinc give the electron to the copper. Copper can give the electron to the silver. The reaction will not be taking place. So zinc is more reactive than the copper than the silver. So that is about the competitive electron transfer reactions. Next, oxidation number. Oxidation number is the number, but it is defining using the oxidation state. Oxidation state is nothing but the formal charge which is present on the element is nothing but the oxidation state. Using the oxidation state, we are writing the oxidation numbers. Okay, using the oxidation number, we can find out whether the reaction undergoes oxidation or the reduction reaction. Let me give a simple example. Then I am going to calculate the oxidation number of an element. For example, H2 plus O2 give rise to H2. H2 plus O2 give rise to H2. In this reaction, you need to identify which one is undergo oxidation, which one is undergo reduction. That is using the oxidation number method. Andre, whether it loses the electron or whether it is gains the electron. Using that, you can conclude that one molecule undergoing or one atom undergoing the oxidation reaction, one atom undergoing the reduction reaction. That is by oxidation number method. Now we need to find out the oxidation number of the hydrogen, I mean the oxidation state of the hydrogen, oxidation state of the oxygen, oxidation state of the hydrogen and the oxidation state of the oxygen in the given water molecule. Some of the rules are there to find out the oxidation number or the oxidation state in the given molecule. The first rule or the first point says that if the element is present in the elemental state, if any atom, if it is present in the elemental state itself, if it is a molecular state, elemental state or the molecular state, it is itself is a stable state. Elemental state or the molecular state itself is a stable state. The oxidation number is considered as a zero. If the atom is present in the elemental state or it is present in the molecular state, a stable molecular state, oxidation number of that element or of that molecule is considered as a zero. For example, sodium, an element of sodium is present as well as it is present as only one elemental state, so the oxidation state is zero. Hydrogen, it is always present in the H2 state, not the H state, H2 state, so the oxidation number of the hydrogen is zero. Oxygen, which is present as a O2 state, so the oxidation number of the oxygen is zero. Fluorine, F2 is present. Fluorine is present as a F2 state, so the oxidation number is 0. Or sulfur is present as a S4 state. Sorry, this is not S4. S8 state, that will be 0. Phosphorus will be present as a P4 state, that will be 0. So the any element which is present in the ground state, I mean atom which is present in the elemental state, or it may be present in the molecular state as a stable one. Oxidation state is considered as a zero oxidation state. Magnesium is a zero oxidation state. Zero oxidation state. Or the hydrogen zero, or the oxygen zero, chlorine zero. That is the first rule. So according to the first rule, if I write the oxidation number for the H2 will be zero, oxygen also will be zero. Isn't it? H2 will be zero, oxygen will be zero for the formation of H2. That is the first rule. Second rule. During the formation of the ion, always group 1 element exhibit the +1 oxidation state, group 2 elements exhibit the +2, group 13 is a +3, group 14 is a +4, and the halogens are -1. For example, for the formation of NaCl, sodium exhibit the +1 oxidation state, chlorine exhibit the -1. I said chlorine is an group 17 element, it exhibit the -1 oxidation state. Sodium, it is nothing but an group 1 element. So Na+1 oxidation state. Sodium ಈಗ suppose sodium Na state ಅಲ್ಲಿ ಇದ್ದು chlorine which is reacting with the chlorine give rise to NaCl ಅಂತ ಹೇಳಿದ್ರೆ oxidation state of the sodium is 0. Oxidation state of the chlorine will be 0 while forming the sodium chloride Na+1 CH-1. Zero oxidation state changing to +1 oxidation state, zero oxidation state changing to -1 oxidation state. Oxidation reaction and the reduction reaction. 0 to +1 oxidation state, 0 to -1 oxidation state. In the case of Na, suppose sodium bare atomic state alli idre, the oxidation state will be 0. Chlorine is present in its atomic state, ಅಂದ್ರೆ molecular state alliде, ground state alliде, so the oxidation state will be 0. By forming the sodium chloride, sodium has to lose 1 electron, so the oxidation state of the sodium is +1, oxidation state of the chlorine is -1. Therefore, always group 1 metals during the formation of the molecule or during the formation of the ion, group 1 metals exhibit the +1 oxidation state, group 2 elements exhibit the +2, group 13 is +3, group 14 is +4, and halogens are -1 oxidation state. And for the transition metals, transition metals, it exhibiting many oxidation states. For example, FeCl3, FeCl2. In case of FeCl3, iron exhibiting the +3 oxidation state, chlorine exhibiting the -1 oxidation state. Charges can cancel each other. Nodi ee tara charges are like this. So FeCl3. In case of FeCl2, one is ferric chloride, another one is a ferrous chloride, +2 and -1. For the transition metals, I cannot say that it exhibits only this oxidation state, but for the transition metals, it exhibiting the many oxidation state. It starts with the +1, it ends with the +7 oxidation state. So +1 to +7 oxidation state is possible for the transition metals, but for the halogens, I said here it is -1, here also it is a -1 oxidation state. So that is the second rule. Yes, it's all. already time up. So I'm going to